Welcome everybody to the second day of the United Nations Satellite Activity Remote Sensing and Smart Tech for Marine Litter and Debris in the frame of the United Nations Clean Ocean Laboratory. This session is a continuation of the session of yesterday, chaired by Victor Martinez Vicente, which was about science and technologies capabilities. My name is Paolo Corradi, and I work at the European Space Agency, and I will be the session moderator of today. So let me start with some event rules. The event will be recorded, so be aware of this, and is now live in the YouTube channel provided. So welcome also to all the participants seeing us through YouTube. The microphone and the camera of the participant needs to be all the time off. So sorry about that, but that's a matter of not creating too much confusion. And if you want to make question, and please do so, any input, any comments, please use the Padlet link provided, also in the registration email that you receive. Our event support will also pass in the chat room of Zoom. Let me remind you the goals that we have for today, which are part of the general goals of the event. The goals of this session, together with the session of yesterday, was to raise awareness about the state-of-the-art capabilities and, of course, also of the limitation of remote sensing. And when we say remote sensing, we would like to highlight this. We speak from ground platforms, so thinking, as you see in the image here, boats, but also, for example, bridge camera or camera in ports or on a pole over a delta of a river, for example. And of course, we talk about aerial remote sensing, including drone, plane, to the extreme version of it, which is satellites. Today, in particular, we'll touch the first two presentations, the platforms of drones and planes. So you will see very interesting application and potential services also based on this platform. The goal is, again, to align some of the users and stakeholders' needs and expectation with what remote sensing technology can do now, and possibly in the short and medium term, as much as we can predict that evolution of technologies can go. And again, one of the goals is to collect your comments, your input, your contribution to this effort that a growing community is doing. So again, please use the Padlet, the link provided. I'm very pleased to introduce the distinguished guests and speakers of today. We will have the first two presentations from Konstantinos Topouzelis from University of the Aegean in Greece, and followed by Eduardo Silva from INESC in Portugal. And following that, we will have two recorded video messages from Nikolai Maximenko of the University of the Y and Christa Marandino from Geomar, Germany. And to conclude, we will have two contributions from Laia Romero from Lobelia Earth, and Kruse from Earthrise Media. So at this point, I would like to introduce the first of our speaker, which is Professor Konstantinos Topouzelis, who is a professor in the Department of Marine Science at the University of the Aegean, and is leading the Marine Remote Sensing Group. So, Kostas, the floor is yours.
Thank you so much, Paolo. Can you confirm that you see my...
Yes, I can confirm. Please go ahead anytime.
Okay. I cannot see you, but it's okay. So I am Kostas Topouzelis. I'm assistant professor in the University of Aegean, Department of Marine Science. Thank you so much for having me here. I'm very honored to be here, and also I have to say that it is really nice that we have all this nice community working on the same problem, on the same subject, on trying to find a solution for the marine litter in the world. So today I'm going to present you two major projects that we run at the University of the Aegean. dealing with calibration and validation datasets for marine litter detection. One has to do with large artificial targets that we place on the sea surface in order to see them from satellites. It is called plastic litter projects. And the second one, it's a coastal marine litter observatory. It's a new platform system algorithm that can detect very nicely marine litter using drone technology. So this is the overview of my presentation. I'm going to give you some information about the early stages of the plastic litter projects, and I will explain to you a bit what we have done the last 4 years for that, and then I will go through the Coastal Marine Litter Observatory, and I will explain a bit more how we can detect the litter accumulation in the coastal zones with drone data, and how the AI algorithms can help us in order to produce data sets that can be used in general from the community. So I will start with the plastic litter projects. Actually, these projects are designed in order to see if we can detect the plastic litter from space. And our scope from the beginning was to explore the feasibility of detecting the plastics using artificial targets. And using these artificial targets, we would like to extract meaningful spectral measurements using Sentinel-2 images, actually. But also later on, other satellites came to the game, and we tried also to analyze their spectral behavior. So in the end, we would like to see if and how plastics can be seen from Sentinel-2 satellite images, and if we are able to simulate the coarse pixel using drone data and drone images. These are the flyers from the plastic litter projects. Now we are in the 4th year, and the last 2 years we are very happy because we run a project that is funded from the European Space Agency. So as you can see, as you will see in the few slides, the project has begun really big, and now we're able to have large targets on the sea surface. So in the beginning, in 2018, we decided with the students of the University of Aegean to create 3 very large projects devoted to the World Environment Day and the World Ocean Day in June, and we created 10 by 10 targets, and we put it into the sea surface. These targets were in the same resolution as Sentinel-2, and the main idea there was to see how we can see the plastics from space. Also, we ran this campaign with drone images. We had several payloads on drones in order to see how the plastics can be seen from drone datasets. These are the first results that we had that time, and the first image that can show how the plastics can be seen from space, from Sentinel-2, and also from a PlanetScope image. Simultaneously, we try to use the drone dataset and to calculate the percentage coverage of the plastics that exist in the pixel of Sentinel-2, and we came up with a conclusion that more or less we need to have at least 35% of the plastic of the pixel, covered by plastic in order to be seen in Sentinel-2 image. In the next year, in 2019, we decided to go smaller. So we created these smaller targets, and these targets were modular. So we were able to put them together and create different shapes. From these different shapes, we try to find out how the targets alter into the satellite images. However, we are not able to have so many data. We're not so lucky due to the cloud coverage and due to the surface of the highways of the sea surface. We ran this project for 2 months, but as you can see, we didn't have so many data. Next year, in 2020, with the help of the European Space Agency, we decided to try to go further and create large targets that stay in the water for a long time. So we tried to have some experiments for that. And we compared the real plastic that we can find into the sea surface with a mesh and an HDPE mesh. And we found out that we are very close to the spectral signature of the two targets, which is very nice because we could use this white mesh in order to create even bigger targets. So also, at that time, we experiment with the different type of targets. So we had an aquaculture cage type target, and we also had a biscuit type target. We put several plastics on them, and we tried different ways to attach the plastics on the targets. Also, in 2020, we tried to create the idea of the large target. We would like to have a very large target that will cover at least 1 pixel. We want to do this because we want to use unspectral methods in order to be able to detect the plastics. And for that reason, we'd like to have at least 1 pixel covered by plastic. So we decided that we'd like to have at least a target of 28 meters diameter. And that was quite difficult to do it. In reality, we had an experiment in order to deploy it on the sea. We found some really difficult problems. However, we were able to overpass them and to create this large target. These are the images from 2020. We were not able to have so many, so we have only 3 images that have plastics in them and different types. And we went through several algorithms in order to do the detection and to see the differences between the natural plastics, the real plastics, and the mesh that we have decided to use. And we arrived to 2021. This is the last experiment that we ran. And you can see that we have two very big targets on the sea surface. One is with the plastic mesh that you saw before, and one is with a wood. So another material that floats on the sea surface. And why would we want to do this? Because we want to differentiate the materials from plastics from any other that exists on the sea surface. And that is nice because we have a mooring system. That mooring system is stable, stays there, and we can attach several targets, and we can leave them there for a long time. Initially, the project was designed to have it for a month there, and to have at least 8 datasets, 8 Sentinel-2 images. However, we're able to keep them for longer time. Here is a result from the satellite image from Sentinel-2 with the mesh target and of the natural debris target, so from the wooden target. You can see that it is easy to distinguish it even in the optical spectrum, and it is nice to see that we do have at least 1 pixel fully covered by plastic or from other material. It was not easy. We had several problems there. You can see the biofueling. We had some problems with the wooden targets, and for 2 days some of the target was sink into the water because we removed these nice buoys that we had in order to keep them on the surface. And it was a bit it was sorry to use the laser point. It was a bit let's say difficult to remove it. It was here with the biofueling, and then we had to take it out. And okay, we also managed to have a mixed target, which means that we have also the plastic mesh and the wood beneath the plastic mesh. So we had the target like this one with plastics and wood. So we can further explore the different spectral signatures from this target. In the end, we were very happy that we have 22 days. So we ran more than 3 months. We had 4 full months with Sentinel-2 drone datasets. We have 22 days with Sentinel-2 drone data and C2 measurements. We ran from end of May until the beginning of October. All these datasets are open, so anyone can see the experiment log file and can download the data and the images that we had from that time. And also, we do have a repository of 18 and 19 datasets on Zenodo, and we are going very soon to have also the last one repository from 2022 to 21. So these datasets are really, we think that they are really good in order to run algorithms for the detection and making larger experiments on the oceans about detecting the plastic. So here we can see that we have several publications. However, there are many groups around the globe that are working on this subject, and we are very happy to give these datasets for calibration and validation purposes. So actually, after some years of looking how satellites can detect the plastics, we have found some factors affecting the detection of the plastics. For sure, we have problems with sangling, with bottom reflectance if they are close to the shore. We do have some problems with the bidirectional reflection. As you saw very nicely yesterday, we need to have very good signal to noise ratio in order to do the detection. And finally, the atmospheric correction is very important. We always want to go further and create a very good data sets, but also an algorithm that can detect the plastic. So for the future plans, we plan to have some inflatable targets that they can stay for a long time and use these targets in order to create larger artificial targets. And the main idea that we have is that we could create large campaigns into several areas in the world in order to have large plastics on the sea surface with the public involvement, with public awareness, and this information can be used for scientists in order to validate and calibrate the algorithms that they create. Going further, as you can see, the plastic litter project, the PLP, started in 2019, and 2019 became really big for us because we were trying to understand all the different problems that exist for the marine litter detection. We saw that there is not only on the sea surface the issue of the marine litter, it's also on the shore. And that time we started working with the CMLO, with the Coastal Marine Litter Observatory, in order to detect the litters that exist on the beach. We had the experience from the drone data on the sea surface from the plastic litter projects, and now we're in a position that we can offer to the community service that comes for detecting the litters using density. So we believe that the marine litter density mapping is very important on the coastal area. We do this with using RGB images as input data from drones, and that is very easy for anyone to collect the drone data. If it has a drone, we have developed a protocol for that. And what we have created is a system that can automatically report through an open geospatial portal. This is quite important because the input to the system is just raw images, and all the rest goes automatically up to the reporting. This is quite important because can support the EU measurements, the MSFD, and the United Nations Sustainable Development Goals. So how the system works, actually, we have drone data, and from this drone data, we have created a system that can do tiling, so can cut the images in smaller pieces. And from these smaller pieces, later on, we train an artificial intelligence algorithm in order to do the detection. Right now, we've gone one step further, and we don't tile the images, but we detect the actual objects, the actual litters that are existing using, again, the AI system. And from point of view of what we want to detect, this is very important in order to know what we expect. We said that we like to have plastics that are at least bigger than a cap of the bottle. So we decided that we'd like to have a ground space distance of 0.5 centimeters. So we have at least 4 pixels into our images in order to detect the plastics. And also we decided that we'll go to the 7 big categories of litter that exist. So we went for this litter, and in the end, we were able to do the detection. Here is an example of the area that we cover with the drone, the drones. This is the reality, and this is the image that we can have from the drone. And once we train an algorithm, then we can do the detection. This is the actual system. The actual system is quite nice. Anyone can log in, then can upload the data, and then execute the algorithm. Once we have this, the result, automatically will take back the reporting of the detection. And here you can see where we already have these data sets in Greece. This is an increasing system, and we hope that very soon we will have cover the most majority of the Greek coastlines, which is quite long. Some more information on the system. Once the data are uploaded and checked, we can see the actual drone images. We can play with them. We can see their specifications, and after that, we run the algorithm. We see the specific part of images that contain marine litter, and if we go a bit more, we start having these accumulation maps. This is quite nice, very important, because later on we can compare these. Sorry, we can use these data sets for comparison with the satellite images. So the next step now is to use this one as an input for the training algorithms of satellite images for doing the detection on them. This is another example. Now we have the points of the actual litter in different categories. We have the confidence of the detection, and we can create these nice accumulation maps of the litter. And also we can define the different categories, and we can just count the litter that exists on a certain area. This is an example of the algorithm. Now this is in case study in Rhynia. It's in a place very close to Mykonos island. We have an image here, and you can see that we can find the different plastics quite nicely, and we can separate it from other material, wood or stones that exist in the area. This is another example in a complicated area. This is in island of Lesbos here, very close to the university. As you can see, there are many places that contain many litters, and here you can see that the algorithm runs quite nicely and can detect most of the litter. This is a video that shows how the algorithm runs. It's quite impressive to see that we can count the litter and we can separate them from a video, and later on we can create these accumulation maps. So to conclude, the Coastal Marine Litter Observatory, it's a very nice data-driven platform. It has a quite impressive, let's say, technology using AI, and also has an analytics part, which is very important in order to run time series analysis. So in the end, it's a tool that can be used for standardization of the data, for harmonization of the data, and to use it in different areas. So it is important to have in mind the interoperability of the system, which is quite nice. This system can work for the MSRT, for the specific goals that it has, and the detection of the D10 C1, and also for the United States for the Sustainable Development Goal of 14.1b. So it can work in large scale, and we think that can be used in order to provide data to EMONTnet and also to the global partnerships of marine litter. These are the two main links that anyone can go and see a bit more of how the systems are working, and can download data or can play with them. Thank you. I will end here.
Thank you, Kostas, very much. Great presentation. A lot of images of impressive target facilities that you have developed. I think quite unique in the world, indeed. And as far as I know, I've been already serving the research of different remote sensing experts in validating their algorithm and in having a reference for plastic in the sea. So thank you very much for that. Please remain with us until the end of the session. There will be the breakout. There will be question. There is already a question for you. So I hope and please confirm that you will stay with us. Otherwise, I can open the Q&A now.
No, I will be with you the whole time.
Excellent. So we postpone the question, and at this point, let me also remind regarding question to use the Padlet. I saw people using the Q&A window. That's also fine, but we would like also if you can please use the Padlet. We can pass to the next speaker. Thanks very much again to Kostas. The next speaker will be Eduardo Silva. Eduardo is the coordinator of the Center for Robotic and Autonomous System at INESC in Portugal, and he's also professor at the School of Engineering at the Porto Polytechnic Institute. Eduardo, at any moment you can take over and share your presentation, please.
Let's go. Maybe I'm out of motion. My camera is off, but let's go.
We can see your presentation is not in presentation mode. It's still just PowerPoint slide.
Is
I guess you can do or in view, or you should have, you know, the button down, bottom right.
The people don't see?
No, I personally see only your presentation, but in PowerPoint mode and not presentation mode. So you just need to make it in presentation mode.
Strange. And then
we're also not hearing you very well at the moment.
I have problems in network now. I don't know. Okay, can I start in the?
Yes, now you're back. Maybe you can try to share again.
let's see if no. I don't know why don't give me authorization to share my screen at this moment.
Well, look that
because we tested before and everything.
Yes, but Zoom is saying now that you have a network bandwidth.
Let me try again. Let me try again.
Please.
Let me try again. Let me try again. Let me try again. And now you see my screen?
I think yes, now we see. And yeah, if you can, well, if you have problem to go to presentation mode, we can see like it was before. Now you have bandwidth low again.
No.
Don't worry, we have some minutes of margin, so this technical problem can happen.
The problem is not the. Let's see. I don't know why this.
Look like you have a low bandwidth according to Zoom.
This happened, but okay, but don't allow me.
Eduardo,
do nothing. Yeah.
Yeah, maybe Caterina.
You can send your presentation to someone or me or Diana, and we can try to run.
Diana, can you run for me, because until now I do the experimentations and.
Yes, I will try to share the presentation. Yes, just one moment.
Sorry for that, but I don't understand why it's happening.
It's no problem. That's part of the game of this virtual telecom. So I think we'll fix any moment. We have anyway minutes some margin in terms of time, so we can catch up. Sorry for the people following. We are experiencing some problem. Apparently, there is a glitch in the bandwidth. We are all scattered basically all around the world, and this problem can happen.
Paolo, maybe Kostas can answer the question in the meantime.
In the meantime, yes. I didn't want just to start now, but let's say we can take a question for Kostas in the moment. Kostas, so there is a question. He's saying, thank you for your speech. In case of marine litter composed of plastic and other components, how you can detect the plastic? So how you can discriminate indeed plastic item from non-plastic items? And also, what about microplastic? There is any algorithm specific for it?
Okay, for microplastics, they are too small in order to detect it using spectral information. So up to my knowledge, we are not able to do the detection directly on microplastics. We try to find the microplastics using other phenomena, let's say on sargassum or on floating materials. So we use proxies in order to go for the microliter. For the rest, for the discrimination, we use mainly different spectral signature for the discrimination, which means that we try to discriminate the floating material with the plastics using the wave bands of the satellite images and their characteristics in the specific bands. So there are several problems for that due to atmospheric correction, due to desampling, due to other interactions. And this is the research of the last years from the whole community, trying to find and consolidate a real good algorithm for doing the detection. The plastic litter projects mainly used for the calibration and the validation of these algorithms.
Okay, thank you, Costa. Thanks for your reply.
Diana, have you?
I see there are still problems. If there's still problem, we continue because there is.
Because I suppose you see.
Okay.
No, it's fine.
Okay.
I think you are already seeing the presentation.
Yes, Kostas, thank you very much. We have other questions we will bring back to you during the breakout session. So Eduardo Silva, please, you can try now to start.
And pass the slides for me, okay?
Yes, it's okay. We can see and we can hear you.
Okay, challenge we have via by ESA, and also to try to de-risk some technology in IPEX spectral image, taking account our experience with the IPEX spectral image, and we start to work with to try to identify with spectral image and we are starting to develop some technology inside of IPEX spectral image to detect remotely the marine litter. We have one project supported by ESA with collaboration with IMAR dos Açores and also Air Atlantic, and to understand if the IPEX spectral image this type of and we developed these campaigns in the
Eduardo, sorry, we have some problem with the audio. If there is anything you can do to improve.
It's better if Diana do the presentation.
You're really breaking up a lot. Sorry, if there is anything you can do. Otherwise,
sorry, because if the condition.
Diana, do you think you're able to take over, because Eduardo is breaking up a lot?
Yes, I will take over the presentation. So
sorry, Eduardo.
Let me just but
in Brussels, in our building is not, maybe I have a problem, I don't know, because I'm in Brussels, not in Porto.
Eduardo, I'm sorry, but we cannot really hear you. Now you're extremely distant and it's breaking up.
Okay.
So
go.
I will move forward on behalf of Eduardo. So the work we have developed under a project that was called Spectrometer for Marine Litter, financed by ESA. The idea was to evaluate the state-of-the-art solution for marine litter detection using remote sensing applications. So the idea was to measure with different systems, with a UAV drone and with airplane, and using hyperspectral cameras, and see the level of resolution that we can achieve in plastic detection. The plastic detection, so the trials were taking place in Açores, in an hot spot in Pin Bay in Faial, and we have set different types of targets made with different type of plastics. The system that we have used were two cameras, a SPECIM FX10 that has a wavelength range from 400 up to 1000 nanometers, and the iSpec S620 that goes to the infrared region for 970 up to 2500 nanometers. So, and the system, of course, was equipped with a GPS, of course, for navigation. We also did some laboratory tests, different kind of characterization of plastics with different type of techniques in order to compare the type of spectrums that we can achieve in this type of techniques. So gather the information from LIBS, that is laser-induced breakdown spectroscopy, FTIR, X-ray spectroscopy, and also Raman spectroscopy. For the same sample, of course, the spectral information is different because the mechanisms that this type of spectroscopic techniques works differently. But the idea was to have a data set of spectral information from different plastics. So regarding the trials itself, so as I mentioned, we used a drone equipped with cameras that did some measurements, some flights over the targets, and we used the airplane that did the same type of measurements. The system was mounted in the bottom of the airplane in order to do the measurements. The campaigns were made between altitudes from 600 meters up to 1,000 meters of altitude, and in the case of the drone up to 50 meters. We also did two different types of target configurations. So one made with single plastics, and we used ropes, white plastic, and the orange plastic was the plastic where the buoys are made, the type of plastic where buoys are made. And we did a single plastic and mixed plastic in order to see if we were able to do the detection. I don't know if you are able to see. So this is the image from the drone that goes over the target. And the image of the airplane also over the targets. So the resolution is completely different, as you can see, but it's possible to see with naked eye. And further, you will see that was able to also be detected by the system. So after getting all this information, we proceed with some processing. The idea was to use different type of techniques for the detection of the plastics. We have used the classification CNN3T and some standard information. All data was normalized to have a zero mean, and the classes had the number of points used to balance the value of the class that was the least point. We found out these interesting results, so it was able to have a good match with an overall precision of 9%, and in the other case with 84%. We also have the results from the airplane, and we have the ground truth information and then the predicted, so with a good match also. The same with other set of data. And this is some spectral information relating the same type of plastic. So the difference between the lab spectra, the same information acquired by the plane at 600 meters of altitude, and the same information gathered by the drone at 20 meters of altitude. There are slightly changes regarding the values, the peak, but the overall image, it's quite similar, which is what was expected. As a final remark of this work, in fact, it was possible to detect marine litter concentrations in water with hyperspectral imaging sensors. The customized hyperspectral imaging sensor was mounted in two different aerial platforms. We were able to perform the campaigns without any problem and develop a processing system able to detect effectively marine litter in water. It is possible, so the study confirms that in fact it's possible to detect marine litter from water, although it's quite difficult to detect different type of plastics. As a future applications of this project, we found out that there is an European directive that mentions that the ports and harbors should detect and monitorize the level of marine litter in their vicinity. And we see here a possible application of this work. So since we were successful in detect plastics concentrations in water with an airborne system, we found out this could be an interesting application. The ports needs now, due to this directive, a better surveillance and tracking of marine litter, and we found this could be a quite interesting solution. So this is a conceptual image that gathers all the information that we can have with the airborne information, also with fixed cameras that could be in the ports, in situ sensors if needed to collect and to detect microplastics, and also, of course, the deep learning tools and techniques that can automatically detect and map the level of plastic in the harbor. And I think it's so. Thank you.
Eduardo, Diana, thank you very much. Very sorry for the little technical complication, but at the end we managed to sort it out. So thanks for the presentation and your result, and looks also you have contributed on a new platform that at the moment is used only from very few groups, which is airplane, that they surely have undisclosed potential yet because they're not explored enough. I can take a very quick question to Diana. I know Eduardo also is going to leave, so I don't know if maybe also we get Eduardo back. But anyway, I made the question to both of you. They're asking the size of the target. And in case, if you want to reply in Padlet, Diana, they also ask about the dates when they were deployed. But maybe you can just very quickly reply, which was the size of their target, please?
Yes, the size of the target, I think it was 3 per 3 meters. So it was the feasible target to do in that place, 3 per 3 meters. Regarding the deployment, this was made in September 2020. 2020, yes. So 1 year ago, roughly.
Which may be to prevent the expectation of the audience, we can already say it was a cloudy day, if I remember well.
Yes, yes.
So maybe people looking for a satellite coverage, maybe they will be disappointed, so we can prevent that. But yes, always they can always try. Diana, Eduardo, thank you very much. Diana, I know you will remain with us until the breakout session, so I'm sure there will be further questions. Eduardo, thank you very much if you can hear us. Sorry again for the issue, but that we appreciate the contribution. No, I'm afraid we lost Eduardo.
You lost Eduardo. Thank you, Paolo.
Thank you, Diana. Thank you very much. Okay, so now we pass to the next presenter. The next presenter is Nikolai Maximenko. We will have a video, a recorded message from Nikolai. Unfortunately, it works against Nikolai both the fact that he's running a parallel event about IMDOS, the Integrated Marine Debris Observing System, and he's also night because he's in Hawaii. Nikolai is a senior researcher at the International Pacific Research Center at the School of Ocean and Earth Science and Technology at the University of Hawaii. And his expertise spans from observation to remote sensing and modeling of ocean circulation and its role in climate and ecosystem. I see we already have the presentation shared. So please, Katarina, at any moment,
Everybody,
I think we
thank
can.
you very much for this opportunity to contribute to your discussion, even though I was not able to join your live conversation. As a supporter of IMDOS, which spells as Integrated Marine Debris Observing System, I deeply appreciate a unique role that remote sensing, together with models and in situ measurements, would play in this comprehensive observing system that is supposed to take a problem under control. You have all reasons to be very proud of yourself. In recent years, you achieved a lot. There were several brilliant research projects that were funded through governmental agencies and foundations. A number of fabulous scientific papers is already large and increasing fast. Recognition of your community effort as a task force within International Ocean Color Coordination Group is remarkable. But I want to be cautious in my optimism because most of these studies were based on controlled experiments and they are kind of preparation for the future. Also, I don't know yet, I don't have yet any satellite-based product that I could use, for example, in my model. In a graphical way, the maturity of observing system depends on overlap between its components. And right now, in my view, remote sensing has little overlap with in situ measurements and more. Two simple illustrations of my cautiousness. For example, in 2011, tsunami generated huge amount of debris, and at that time, satellites could not help us much. They detected thick mats of debris right after tsunami, but a few weeks later, when debris dispersed, it became invisible to satellites. In the meantime, it was washing up on North American and Hawaiian shorelines in large amounts. I'm asking, would we be able to see this tsunami debris today? I'm not sure. Another example is last December, a huge cargo ship lost more than 1,800 containers, cargo marine containers, and presence of their content was confirmed by observers on northwestern Hawaiian Islands and also by sailors going north of Hawaii. Fortunately, they didn't reach main Hawaiian Islands, but we know these containers were out there, and with the best effort, we were not able to see anything through our satellites. Now, the hard part. Why our satellites cannot see marine debris the way how we want it? There are many technical reasons, but combined together, I would say existing satellites were not built with marine debris in mind. They are mostly designed for targets on the land. What can we do to mitigate these limitations? First of all, I think we should be real. We should be realistic. We need to objectively evaluate capability of satellite missions and decide honestly what we can and what we cannot do using their products. Then we can also check the entire line of processing of the information, from accuracy and precision of sensors to onboard processing and on-ground quality control and product production. As a last resort, we can also try to switch from detecting small debris items to detecting larger ocean phenomena, such as windrows, slicks, and eddies. This will not solve all our problems, but it will help us with some of them. But speaking of a radical solution, let's think about designing and building a dedicated marine litter or marine debris satellite. 5 years ago, I would not even say this. But now we are in a totally different situation when society is very concerned about marine pollution and governments and companies are ready to invest big money into this problem. Additionally, commercial satellite companies are very active and they may be looking for new applications. Thank you very much and good luck with your very important activity. Aloha.
So our thanks to Nikolai to share this very important message. It's a message, of course, of what are the limitations nowadays about satellites. Of course, as we anticipated, remote sensing is not about satellite, but we always emphasize this aspect because that's the ultimate tool we might have. And it's very nice to see also Nikolai look into the future and to the possibility that indeed are presenting closer and closer respect to when 5 years ago this discussion was started, and it was really a nice and stimulating brainstorming, but we were not imagining probably to also arrive today at the point of research and development that has been done so far. So that's for all of us very stimulating, and I thank you again, Nikolai. And I want to remember that Nikolai is the initiator and the leader of the integrated marine debris observing system, where the approach of remote sensing is an integral part, of course. So as one of the many tools that we need to monitor marine litter. Remote sensing, we know, it will not be the only solution, but it will be part of this integrated solution with the ground measurement up to satellites. So again, thanks. Please, if you have any question for Nikolai, also is not here, as you understood, but you can leave it in the Padlet, and we will try to pass to him and so to get and publish a reply. Now we pass to the second recorded video of today, recorded message from Christa Marandino. Christa is a researcher working at the Division of Chemical Oceanography at the Helmut Center of Ocean Research in Kiel, in Germany. Christa does research in analytical chemistry, in atmospheric chemistry, and chemical oceanography. She's also leading the effort of the OASIS, which is Observing Air-Sea Interaction Strategy Group, who is another United Nations satellite activity currently running in parallel. So if you will have time, once we are done, you can also join and follow their very interesting contribution and events. So we should be able now to launch the video of Christa. I see now coming online.
Observing air-sea interaction strategy and our mutual interest in the clean ocean activities. I'm Christa Marandino, and I, along with Megan Cronin and Seb Swart, co-chair the OASIS SCORE working group that is taking a systems-as-a-whole approach for making surface and boundary layer observations relevant to the Earth's energy, water, and biogeochemical cycles. OASIS was endorsed as a UN Decade program and has teamed up with the Surface Ocean Lower Atmosphere Study, or SOLAS, to convene our satellite activity. To understand and predict the ocean's influence on weather and climate, we need to accurately resolve air-sea heat fluxes. The first step of developing the OASIS is determining what processes need to be observed, their sampling requirements, and uncertainty specifications. The color coding here shows what accuracy the fluxes must be to achieve a 20% signal-to-noise ratio. But we also know that heat fluxes are not the only air-sea flux that is critical to understand. Others include water, carbon dioxide, and other trace gases, such as N2O. Our working group has its roots in the Ocean Ops 19, the once-per-decade strategic planning conference. Megan was a lead author on a community white paper, Air-Sea Fluxes with a Focus on Heat and Momentum, that had 29 co-authors from around the world. She saw other community white papers led by the carbon community, the weather community, the satellite communities, and by different regionally oriented communities like the Tropical Pacific Observing System 2020 project and the Southern Ocean Air-Sea Flux community, among many others. There were more similarities than differences in the pitches. Most recommended enhancing existing observing networks to provide more co-located observations. Many recommended using new emerging technology, like uncrewed surface vehicles, to expand the coverage of the global network. Nearly all discussed the importance of capacity building and sharing, mentoring, training, and education. All recommended developing best practices and making data and products more findable, accessible, interoperable, and reusable. To make any of this a reality, it was clear we needed to take a systems as a whole approach. This was the driving motivation for forming a SCORE working group. As one of our first actions, we wrote a successful proposal for OASIS to be endorsed as a UN Ocean Decade program. This is bottom-up science and the community coming together to make transformational changes to ocean science for sustainable development. One thing that is perhaps different than other SCORE working groups is that we have administrative help from the Consortium for Ocean Leadership to help with communications, including a website, Slack pages, newsletter, webinars, and telecoms. Their support is coming through Ocean Ops activities.
Liebt es hier zu trinken. Kann nicht draußen trinken.
Regarding this Clean Ocean event, we all know that the human footprint is
Sabine, can you mute your microphone, please?
Such as the open ocean. I show you here just a few examples of this: the spread of surface ozone pollution, the occurrence of harmful algal blooms, and the reach of the global shipping industry. These topics and many others have a key air-sea interaction component. This UN lab is a crucial but relatively unique opportunity to allow the air-sea interaction community to reflect on how our traditional scientific topics interface with ocean pollution and hazards. To facilitate this process, we have convened the Oasis for a Clean Ocean event with the aim to develop a roadmap for how observations and understanding of air-sea interactions can support a clean ocean. This clearly involves the satellite community. Our event has 3 sessions with associated main questions. The first session is on impacts of marine pollution. We ask here, what are the effects of pollution on air-sea biogeochemical processes, harmful algal blooms, and other processes? Session 2 is about techniques in observing or understanding marine pollution. We ask here, what are the observational and model tools used to support a clean ocean? These observational tools include remotely sensed as well as in situ observations. We also ask what is missing from this set of tools. In session 3, we want to explore the idea of an OASIS strategy for a clean ocean, and for this we ask what specific steps should the UN Ocean Decade OASIS program take to support a clean ocean. We hope to engage the community in discussion on these topics in order to develop a roadmap for OASIS, SOLAS, and other air-sea interaction interested folks to move forward. Input from the RSMLD and IMDOS sister events is welcome and encouraged. Please watch the videos posted here from our event on YouTube. Here I make one final point to support the discussion on OASIS for a clean ocean. This is the OASIS organizational chart showing how we seek to work with community members across 5 theme teams. Each of these themes, developing the network and model design, capacity building and sharing, UN Ocean Decade, the best practices in interoperability, and fair data model and OASIS products can be tapped to support a clean ocean, but we need engagement from the community to help us learn how. Please join our network at airseaops.org and be part of this community effort. Thank you very much.
Thank you to Christa, and yes, it's the same said for Nikolai and Valid. Please put your question on the Padlet, also for Christa. Indeed, I would like to highlight the fact that our event, the IMDOS event and the OASIS event, were proposed and selected by the United Nations Clean Ocean Laboratory as a coordinated effort covering, in fact, the marine litter topic. So we count to continue this cooperation with the IMDOS and the OASIS for the future. So that's why you see the intervention of representative of the IMDOS and OASIS group in our event, as well representative of our event, like Manuel Arias was presenting in their events. And now I think we can proceed with the next speaker. The next speaker is Laia Romero. Laia is a ISAT Group Director of Operation and Strategy, and she's also responsible for the Health Observation Service business unit of Lobelia Health. And her work is focusing on satellite data for climate action. In the frame of our effort of remote sensing of marine litter, Laia is particularly focusing on the microwave-based exploitation of satellite images, in particular SAR, combined with artificial intelligence. And today she will introduce this, and also an important initiative which is about developing a database, OceanScan, that might be of great support for all the research. I see Laia is already connected. Hello, Laia. You can share at any moment your presentation. Yes, I can see it and is in presentation mode, so anytime. Thank you.
Okay, thank you, Paolo. I have two parts of my presentation. The first one is on the use of SAR for marine litter detection, the work that we have done so far, where we are, and the next steps. I will try to be very brief, and then I will present OceanScan, which is an in situ and remote sensing database for remote sensing studies of all, like, that apply to all of the presentations that we are seeing today and also yesterday on the development of new technologies for the detection, study, and analysis of marine litter and debris. So the first part of my presentation is on my personal research field, so to say, which is on microwave and on the analysis that we have done so far. So as you have seen, most of the projects and ongoing initiatives focus on optical data. Well, we have already seen also thermal, and in the optical, there are many different technologies used, but there is little on microwave, and our objective in a way, a few years ago when we started, was to understand the sensitivity of the radar signal to the presence of marine litter. We started with plastic, and we are now looking at plastic and also debris such as wood and others. So the importance of this is that SAR works in an all-weather, night and day, wide swath, and it sees through clouds. So it is very, very useful and applicable to any maritime study, anything that we look on the ocean, because of clouds and because everything on the ocean is moving. So by using SAR, in this case a radar, with other techniques, we can greatly increase the temporal coverage and the spatial coverage of any measurements that we do. So, okay. So as I was saying, our objective was to demonstrate the potential of this technology and set up an automatic identification of marine litter in SAR images following a pixel-based approach and using AI. So for that, we have been facing in the last years three different lines of work. One is the generation of ground truth correlated to SAR acquisitions, because as we will see later, it is very difficult to have ground truth to set up any kind of studies, and we have seen it in other presentations these days. Also, to identify the SAR features that are well mapped with the presence of marine litter, and we are looking here at texture analysis, intensity, and polarimetry, and also to develop an expert pattern recognition approach to identify these marine litter signatures. So the preliminary, well, a bit on the methodology. So we are looking at patches of marine litter in the ocean, and also in the same images at areas with no marine litter present. And we extract features, and when we run a principal component analysis to see which of these features are explaining the largest percentage of the variability of a data set, in this case of the in situ observations on the ocean. Just as an overview of the methodology, I want to be very quick. And the preliminary results in the Balearic Islands, and I think Manuel actually mentioned a bit these results yesterday, were quite positive. We have a good balance accuracy for a couple of methodology. A total of 1,794 pixels were labeled as plastic in that study, and over 6,000 were labeled as non-plastic. And these good results were obtained, but the reality is that these results are very adjusted to the observations that we had in the Balearic Islands, and that we cannot yet apply this anywhere else because we require a lot more of in situ observations to be able to test in many different conditions, to also understand signal to noise ratio analysis that we are having, etc. This is the Mireia project, and you can find it online, and there is more information online. We tested this model on different events, such as Euronews, because there was a news on a very large patch on a dam, and we tested our classifier on this completely new data set that had not been part of the study, and we were able to see very clearly, well, there's a lot of noise in these images, but it is exactly the same one in the first one and in the second one, and what you see different is the actual detection of the litter that corresponds to the upper band in the blue lines, and also the lower band in the red lines. So actually we see that the sensitivity in SAR to marine litter that we demonstrated in the first study, it is actually applicable, because the more that we check, the better that we see that it can perform. Some other ongoing work, because the project ended at the beginning of this year, and we are now working with GFZ and also GNR on the detection and tracking of large patches. So a bit building up on the processing chain that we have already built for the SAR, we are using it. This is a patch in the coast of the Balearic Islands in Mallorca, and it is a patch that we detected, that we only detected in SAR because it was not visible in optical because of the clouds. It is a patch after a storm, and we continued. We could see this patch moving in this area of the Mediterranean, and we are studying how we can detect it and also track it with currents, with models of currents. And we are doing the SAR part, and GFZ are doing the high resolution part with optical. Another ongoing work is the exploration of proxy features that lead to large accumulations in the radar signal. This is a work that we're doing with PML, and the project is called Frontal, and it's based on ocean fronts. And what we are looking on our side is on the sensitivity of the radar signal to this type of discontinuities that we see. You see here some inflection points in the SSLA, in the significant sea level anomaly of Sentinel-3 altimetry, and how these correspond to some thermal fronts. In this case, they coincide very well, but it is not always the case. Thermal fronts that we see with other technologies and models, and because of clouds, we do not have the information on the thermal fronts everywhere, and so the radar can help. And so we are exploring also these proxy features. The next steps for us are clearly the increase in the training data set with more observations. We see the potential. We see, as our colleague was saying yesterday, it is not easy, but it is feasible to detect something, but then we need to know what it is exactly. And so with SAR, I feel that for what we know so far, it is a bit easier to classify different materials than with optical, because we do not rely so much on the optical conditions. So we would like to increase the training data set, and we would like to test the potential of SAR for discriminating. For that, this is Topouzelis Costa's experiment that he just presented. And so this type of artificial targets, the use of drones, the use of planes, like to build a larger data set is much needed to advance in this technology. So I will go to my next presentation, which is on ocean scan, and that tackles specifically the problem of not having enough training data, enough data sets. Wait a second. I hope I can share it. Okay. Can you see my presentation for Ocean Scan?
Yes, we can see already.
Okay, thank you. Thank you. So, Paolo, thank you for having us presenting Ocean Scan in this session. Ocean Scan, it is a very special project because it is a community project. It is led by Lobelia in this case and ISARETSAT, with the participation of partners, GFZ, Prototype, and the University of Versailles. But it is a project for the community that was born from the need of observations for the advancement in the remote sensing world. So we started this project a year ago, and we will be having the online platform at the end of this year. The objective of Ocean Scan is to provide tools for the community. This project will always be open to researchers and free of use. And we are now building what it is, a marine debris database from Earth. So in situ, ground in situ observations of marine litter and debris, and space with satellite missions. So we started with these critical requirements for any given project on remote sensing. And these ones here correspond to our first project on SAR. And if you read them, they can be very similar probably to your own requirements for in situ data. We are talking to all of the teams that are working in remote sensing and marine litter, and we are collecting this type of requirements. So in this case, this is an example, but it is important because it is the starting point to have positive, so presence of plastic and non-presence of plastic, to know the extension of the plastic patches, and to have like large accumulations, not only like one plastic bag or one, like this type of databases are great for awareness and for many different things, but not for the remote sensing analysis. So we need large patches. We also need the error in geolocalization to be minimal. And this is very, very important because you cannot find like corresponding satellite imagery if the lat long is not precise. Also the timestamp, every satellite mission has an orbit or follows a track, or the imagery has a particular timestamp, and we need to find this matching Earth observation imagery and signal with the in situ observations in the field to be able to validate, to calibrate, to understand what we are seeing from satellites. The number of samples. So for any AI is blooming in this field, and it is obvious, like the reasons why are obvious, but we need a large number of samples to be used in AI projects. The data should include some information about the total extension of the patch. The data should include the type of objects that are comprised in the patch, the type of material, the mean depth of the objects, whether they are submerged or not. And I hope this sounds familiar to what we have been seeing in the last presentations and also yesterday. And finally, a picture. When we need a picture where we can discriminate what it is. So because it is not even if it's available in high resolution. Yeah, but we need to be able to really say this was marine litter of this type, and this is what we are looking at. So we did we compared, or we had a benchmark. We did a benchmark of all of the databases that existed, and we saw that there are many databases, and we didn't want to make one more database. We wanted to use whatever existed that was useful for remote sensing. And we saw that many included super interesting information, but were not compliant. None of the existing databases, these ones are the main ones, but there are more. The list, the benchmark is quite large, did not comply with the needs of having land accumulations, but also water surface accumulations, precise geolocation, the observational timestamp, the data provenance, where they come from, so that we can actually credit or work with other researchers that are taking these observations, and also the way of accessing these observations, which for AI projects need to be super easy, API-based or similar, to be able to build a data architecture. So what is OceanScan? It is a global in situ marine litter database that supports remote sensing research. It is interoperable with other data standards, and this interoperability is shared with relevant initiatives, and we are building on top of UNEP, on top of OSPAR, on top of anything that exists so far, and we are looking at it at the task force, that we need to take into account, and it will be both ways. So what we produce in a standardized format will be interoperable for other databases. It is a well-curated marine litter data in a unified format, and the data sets are aggregated in what we call campaigns, and they have automatically an DOI associated to them and are stored in Zenodo. So to provide with full transparency of the data that is being ingested and to keep the full ownership. It is accessible via an API. It is an international cooperation effort. It includes a web interface, a mobile app, and a database. And there is a very strong code of conduct that I will mention. This is the mobile app. It is open source. It is a mobile app that is very easy to use and that follows the requirements that we mentioned at the beginning. So you are at a certain place, you open the app, it works with Android and iOS, you take a picture. Once you take a picture, you decide on a visual inspection level whether what type of litter it is, if it's one large single item, an accumulation, a patch or a filament, and you can take this picture from anywhere. And even if you don't have reception, once you have reception again, the GPS will keep the timestamp and also the geolocation of that picture, and this is automatically uploaded into the database. You can also put the type of items that you are seeing and also an estimated quantity. So logic workflow, picture of observation, time lat long, visual inspection, litter type, estimated quantity, DB, upload. This is from the app. Now we are working on the uploading from the web interface on existing data sets that we can already start using. The code of conduct, this is available on the, please go to oceanscan.org and send us an email. This will be available, everything is available on the website, but the main idea is that it is open, that the ownership is kept, that the data provenance is always kept, that the researchers can actually apply the terms of use that are needed by their teams, and that this is useful for everybody, and by sharing we can actually all advance in this field. And then I would like to show you very briefly a demo of what exists. Okay. I will share the screen. Trying to be super fast. Okay. Do you see my screen?
Yes, we start now.
Okay. So this is in development. This is the development website. We can log in. Once we log in, well, this is the homepage. It's in development. Huh? You will see the places where you see where there are observations. We included a few databases to test and to actually define the UX. And I want to look at the marine litter watch data set. We included this data set just for development purposes and integration. So the first thing that you see, I can also edit this. The first thing that you see is like the campaign, which is like the entire data set, what it the area that it covers, and who are the participants, and the area, and the license, and this type of things. And then when you go to data, you see, hopefully, okay, thanks, a number of observations that are inside of this data set. And when you click on each observations, what you see are the satellite missions that have tracks or images that are matching each of these observations. You also see the material types, because in this case they are available, and you can click in any of these, and you will see all of the tracks that are available. The participants in this case is Marine Litter Watch, and I wanted also to show you the filters that we are applying. So, which include ground truth images, and by ground truth images, it means that it is validated, so that what these observations are of high quality, are like, we should be confident on these observations, that on what we see on the visual inspection from these observations, whether they are the single large item, or if it is an artificial target, if it has a small group of targets, if it is a patch, a filament, and the type of material, to be able to filter. And so you will be also able to filter by satellite mission. And that's it from our side. I hope that it was clear, more or less, and that I managed to convey the message. Sorry for taking so long.
Yeah, thank you very much. Well, first of all, for introducing the microwave remote sensing domain for Marine Litter, and but also for your great effort and commitment to bring ahead something that all researchers are looking for, which means a database of ground truths, data, and images to work on. So thanks for the presentation, also the nice website that you presented in details. I hope the interest participant will respond also to your call and registering in OceanScan. You will find the link in the Padlet page, so please go there and also put your comment. Now we need to progress quickly. We have our last, of course not least, researcher and presenter is Caleb Kruse, and it's big thank you first of all to Caleb, who is in California, so you can imagine what it means presenting in the night now for him. And let me introduce Caleb quickly. Caleb is a researcher at the Earthrise Media, focusing on artificial intelligence and remote sensing to better understand environmental changes. And prior to that, he was studying oceanography at Stanford University, and before leading the machine learning team at Leap Motion, focusing on computer vision system applied to virtual and augmented reality. And today, Caleb will talk about detection and monitoring of waste sites in Southeast Asia using Sentinel-2 data. So please, Caleb, if you can share your presentation and start at any moment. Thank you.
Perfect. Thank you, Paolo. Yeah, so I'll be sharing some of the work that we've been doing. I would like to mention I'm with Earthrise Media, and this work has been supported by the Minderu Foundation. And I know that this conference is focused on marine debris, but wanted to share the work that we've been doing on terrestrial waste detection and showing some of the potential links to the ocean debris problem. So first, what are we looking into? What are we trying to find here? Well, here's an example on the right and the left of what these waste sites can look like. On the left, you can see these sometimes astonishing aggregations of waste where it's just piling up in these huge mounds. And on the right, we see sort of more of an informal site, more of maybe a dumping ground or something like that. And both of these are very important to be able to detect and ultimately then monitor. Ideally, we want to be able to do this in sort of a scalable way using remote sensing data to be able to find these locations. And so it's helpful to know, what do these actually look like from space? Well, here's what they look like in high resolution data. And there's, a very different story between high and low resolution, but it's helpful to understand at the beginning what it looks like in high res. So in each of these patches here, there's a dump site in the center. So we've got, one here and one here, and you can see that, in high resolution imagery, they somewhat have some defining characteristics. It seems like it might be a tractable problem to be able to find these things. But then as we, so they're highlighted the locations of these dump sites. But then when we move to Sentinel data, we're using Sentinel data because this high resolution data, it's not publicly available. And then also if it is available, it oftentimes is not refreshed very frequently. So we've been using Sentinel-2 data. And of course, the product is a lower resolution. So instead of the 30 centimeter per pixel data that we were seeing before, now we're roughly sitting around 10 meters per pixel for the highest resolution bands. And you can see that it becomes a really challenging problem to be able to identify the locations of these waste sites. So these are the same sites that we were looking at in the previous frame, but just seen through Sentinel. So we're trying to make an algorithm that's able to identify these waste sites and doing it in Sentinel data so that we can kind of have global coverage and update that through time. So I'll talk a little bit about our methods. Now, I don't want to go too deep into the methods, but just a high-level overview of sort of what's the architecture of this system and how does it work in practice. Fundamentally, we're training neural networks to be able to classify the presence or absence of waste. And with all applications of this nature and algorithms like this, you got to start with the data. So we start by selecting a set of known waste sites. Now, our data set is growing. We kind of turn an engine every time we detect new data sites that have been confirmed. We can add those back into the training set. But in the beginning, we started with only 10 known dump site locations, so a very small amount of data. So this is a kind of an example of what the positive class patches look like. Then we also collect a large negative class, sampling uniformly across the region of interest, but also at a heavier density where the networks might be confused. And then we train a neural network on this. So what does the architecture of that network look like roughly? So the first step here, let's see. There we go. So what this looks like is we take each of those patches that you were seeing previously. And those patches, of course, have red, green, and blue wavelengths, but the Sentinel data stretches across 12 bands. So red, green, blue, and a number of infrared bands. And we take that stack of information and we break it apart into each individual pixel. And we also look at that pixel across time to understand how it's changing. And for each of those pixels, we then pass the single pixel to a pixel classifier. And this pixel classifier is mostly a spectral classifier to be able to evaluate the presence or absence of waste. And so the inputs of that are going to be a single pixel of sentinel data, and the outputs are going to be a probability from 0 to 1 that the pixel contains waste. So here's how it works kind of in practice. On the left here, you can see an image of a pretty easy dump site detection. You know, this one is fairly large and situated within a forest. But you can see on the left, this is the waste site, and we break apart this patch into each of its individual pixels, pass those to the neural network, and then the neural network produces its outputs on the prediction of whether the waste is present or not. And so in this figure on the right, I'm representing any of the neural network outputs in blue when it says that there are no waste, and red when it thinks that there's a high likelihood that waste is present. And you can see it's pretty easy to rule out all the forest, right? The network does a very good job of that, but it's also doing a good job of, you know, identifying that this, you know, bare earth or the road is not a waste site. So now that we have this pixel classifier that seems to be working fairly well, we can just deploy that at a pretty large scale. So here's an example of running the pixel classifier on every single pixel in Java. And the outputs of that are, it's sort of like a heat map of waste presence. Now, I think it's important to note in this figure, this is roughly what those outputs look like from a heat map perspective, but I've scaled this image so that we could actually see it. If we didn't scale this image, we'd actually have more very like kind of little speckles where there's actual kind of these sites, the waste site where waste is aggregated. And so the outputs from that look like this. From the heat map, we detect areas where there's a lot of heat, kind of aggregations of it, and establish those as waste site candidate locations. So this all sounds great. If the pixel classifier does a good job, it should, you know, be a good system. And so we were excited, had run this on Bali and then ran it on Java. But then I started to see sort of a confounding result. So on the left here, you can see in these little blue dots, I was noticing that the pixel classifier was identifying lots of these white roofed buildings. And I was thinking like, come on, you know, I'd sample it in the negative class, and I was wondering what was going on and why it was detecting those. And I was pretty confused until I looked at the Google Street View data and I noticed, oh, these are all plastic greenhouses. So the model probably is picking up a large signature of plastics. And in this case, because it's a single pixel classifier, it has no ability to discern that this is actually a greenhouse versus a waste site. So clearly we need to bring in some structural information to sort of help this classification process where you're not just detecting a greenhouse roof because it's made out of plastic. So we have one final neural network that takes every candidate site from the pixel classifier process that I described previously, takes in one of those candidate sites, generates a patch again around the candidate site. And in this case, it's you know, taking in spectral information, temporal information, but it's also incorporating structural information. So it takes in the patch and it just makes a binary yes/no classification that this patch does or does not contain a waste site aggregation. And so for the previous example, it makes it very easy for this patch-based classifier to then say, no, this is a greenhouse. It's clearly not a waste aggregation. So we have kind of this multi-layer neural network system to be able to do these classifications. And so I want to get into a little bit about what we're finding and the results so far. So we've run this model on all of Indonesia to this point, or this model system. And it's amazing, like that's analyzing 163 billion pixels. And we found 330 confirmed waste sites. And this is a significant improvement over what was previously known. Some, you know, data on this is always hard to come by. Maybe it's hidden away in some government database, but in terms of publicly available data sets, there's, you know, only 117 sites that are known of on OpenStreetMap. And even of those, a lot of those are either no longer active or not necessarily accurate. So it's amazing to be able to run this algorithm and say, in 2020, here's the 330 waste sites in Indonesia that we detected and are active. I think that there's two interesting notes to highlight here. One is you're analyzing 163 billion pixels to find 330 waste sites. So it just shows that like it's a problem that's totally intractable to do by hand or with human intervention directly. And so it's nice to be able to see these neural networks sort of pick up that task and be able to, at the very least, reduce the search space for the human validation. And then on the second point about human validation and what these dump sites, these detections look like, I can say with confidence that every detection we have in Indonesia is an active dump site because we validated all of these by hand. We look at high resolution satellite data or Google Street View data or other sources to say actually confirm whether this is or is not a dump site. But I do know that we are still missing some. And so we hope the model gets better over time to be able to detect different types of dump sites. But here, there are no false positives. We realized this was working pretty well in Indonesia, and so we decided might as well just run it on all of Southeast Asia. So now we're analyzing more than 500 billion pixels, and we've detected 918 waste sites across the countries of Southeast Asia so far. Again, I think that the model will strongly improve in geographies outside of Indonesia. We'll get much more sensitive to more dump sites as we add in a little bit of training data from this new detections. But it's pretty promising to be able to see that this model that was trained on data almost entirely from Bali and Java is able to expand throughout all of Indonesia as well as all of Southeast Asia. It'll be interesting. We're going to try to scale the model to more and more geographies. But it'll be interesting to see how it does as the geographies get more distinct from the Southeast Asia kind of type. So the next thing that I want to talk a little bit about is we know the locations of these waste sites. And so the question is, can we do anything with it? What else can we do that we have now that we have this data? So the first is site monitoring and monitoring of the boundaries of the waste site. So here we run the pixel classifier for every single detected site. We run it again. And you can see, you take in an input site like this, you make those predictions, and you can find the area of the dump site that's actively has waste, not just like bare earth. And then you can build a contour around that. So that's interesting to understand the site footprint at a single point in time. But the beauty of Sentinel is we have data that stretches all the way back to 2016. And so we're able to run this pixel classifier across all of the scenes of Sentinel data. We actually are running it on a quarterly basis now and see how that site footprint has changed through time. So here in this figure, it's hard to see because it's so small, but roughly the trend is in red are the pixel classifier outputs that are a high likelihood of waste. And you can see between 2019 and 2020, the size of this patch has increased pretty substantially. And so this is what it looks like in practice. You can see, the waste sites have, this single site has increased in size by 500% since 2019. And then specifically, you can see actually how is it expanding? Like which direction is it expanding? And here, I think it's really interesting. You can see that the waste site is expanding, but in particular, it's expanding towards a river right along the left side of the dump site. And that river is very close to the ocean, and you have to say like, hey, this might be a real risk for there to be a lot of leakage from this waste site. So that's one element of additional things that we can do after we've detected sites. The other thing is we can pull a lot of really interesting, rich metadata from other sources to capture a more detailed picture of the site. So we can query them based on their size. You want to only look at big ones, small ones, the change in their footprint, the land slope, the soil type. But in particular, one that's quite interesting to me right now, and I think will be functionally very useful, is the distance to a waterway. So if you think about Southeast Asia, there are just waterways all over. There's, if you throw a dart at Indonesia, you're likely to land pretty close to a waterway. And we see this in the distribution of dump sites as well. The majority of dump sites are falling within 100 meters of a waterway. And I think that this could be a really interesting source of ocean pollution that is worthy of study. And I just want to walk you through just a couple of examples of this. Like, we're seeing a lot of waste sites like this. And the examples I'm going to show you here are all just taken from Java. Like, these sites exist throughout Southeast Asia, but clearly you can see how the waste sites here are just essentially they're spilling over into the rivers. And you have to think that this is a source of some portion of the ocean pollution that we're actually seeing and trying to monitor. You know, again, here's another example, and you can almost just like envision like the monsoon season comes, the river flows, and it takes away the trash and flows directly into the river. And so it's really interesting that when you like analyze 500 billion pixels to find 900 sites, you then might be able to filter that down and say like, these are like the 17 or 20 sites that are kind of the biggest offenders. Like, these are the ones to focus on. If you're going to try to do remediation or kind of barrier enforcement efforts, then these are the sites that we think would have the greatest difference, make the greatest difference for the ocean pollution type of a problem. So this is just a handful of examples. These kinds of sites are everywhere throughout Southeast Asia. So the last thing that I wanted to share is we're working to make this publicly accessible. We want this to be a platform that where the data is open and usable. And I'll just show you, this is what we have in development right now, where you'll be able to not only you'll evaluate the detections and be able to take a look at the sites that have been identified. You'll be able to view how they're changing over time interactively to be able to understand how a single site is changing. You'll be able to query the distance to a waterway for the site, and then finally to be able to surface those other site attributes. So that, in a nutshell, is sort of what we're working on the waste site detections on land, and hopefully pairing that more with the ocean debris issues. I'd like to, feel free to reach out with any questions on the work. My email is listed here, as well as Fabien Laurier at the Mindru Foundation. Feel free to reach out to us with any questions, and thanks for having me today.
Caleb, thank you very much for your very interesting presentation. I think there is definitely a continuum in monitoring for plastic waste on land close to water bodies and water bodies like the sea. So it seems to me that for the big picture, we will need to combine, or let's say fuse data from these two monitoring targets. So that's, I think, is a very important contribution. Thank you very much, Caleb. And please, if you can also remain with us, of course, like with other speakers, we are opening now the breakout session. We are running a bit late, but we have about 15 minutes to take some of the questions from the participants. I would like to start in the order of the speaker. From the Q&A window, we have some question from Maurice Muller. Is asking if you are aware of any hyperspectral camera system small enough to be put on the consumer drone like the Phantom 4 or similar. Or do they only exist for larger drones such as Matrix 300? So maybe I can ask this to Kostas and Diana, for example. Kostas, maybe you want to reply for this? You can start, please.
Yes. As far as I know, there is no hyperspectral camera that can be used with Phantom or this type of drones. We need to have larger ones in order to carry them, and this is because the hyperspectral cameras right now are quite big, and because they need to derive many wave bands, which means that they need to be quite large. Up to now, I know that there is commercial cameras with 8 bands, but we're far away from having, let's say, 100.
Yeah. Okay. I think there is also another question that could be still for, I think it's for you, Kostas, again. Well, is regarding, isn't the objective to distinguish plastic from seaweed? Why you didn't include the seaweed on a test patch? So I think I referred to the target. So Maybe you can elaborate about integrating seaweed vegetation.
That would be actually nice to have seaweed and put it in a large target. It is something that we can do. However, we need to have a large amount of seaweed in order to put it on the target, and it has to stay there for a long time. There are some, let's say, difficulties in order to do it, but it is a possibility, yes. So in the beginning, we started with only plastic. Now we know that we need to have many other floating materials, let's put it this way, that they are natural. One of those, it was wood, because it is easy to stay on the surface. And then we can go to other ones, like seaweeds. I have to say that even the woods, due to biofouling, in the end, it was hard to keep them on the sea surface for 2 months.
Yes, can imagine how much can be more difficult, and I think for the audience to handle things in the sea and at experimental level. So thank you, Kostas. I think we can also ask another question now to maybe Diana and Hugo. I see is also there. I think they were referring to your presentation, I'm not sure, but anyway, they say in practice it is possible that the plastic is scattered rather than patched together. So how would this technique handle the result if the same amount of plastic used in the test were scattered and not, like, you know, accumulated in the target? So what do you think? Yeah, if you can elaborate, please, about you know, very dense continuum plastic target or scattered, so dispersed plastic items.
Yes, regarding our experiment.
Hugo, we cannot. We're very, very far. Sorry.
Sorry. I was saying that regarding our experiments in the forest,
still not good.
Better now?
Better, yes.
Okay. What I was saying that in our experiments in the source, the plastic was not. If you compare, for example, with Costa's targets, the Costa targets are more dense than ours. So the plastic was not completely connected. So it was a dense mass because the targets were big, were 10 by 10 meters. But they were a little bit scattered a little bit in terms of connection between the bottles and between each of the elements, so to speak. So you have water in between the plastic targets. So, but the algorithms might be, you label the images to be able to train the algorithms for the detection. And therefore, the algorithms were trained also based on that, and also based in what was water and what was the plastic target. So the idea, when we then extrapolate for the detection, is that it's able to detect on those conditions that was the training. So I would say that if the plastic is scattered, even so he's able to classify the plastic, I would expect him to have less precision and less recall in the detection.
Okay, thank you. I hope everybody could understand. They were breaking up a bit, but I think was hearable, at least was for me. Thank you, Hugo, and Diana, for your reply to the question. I would pass now to some question from the Padlet. I see a question from Laia, sorry. What is your opinion, Laia, on synthetic marine litter data made from in situ verified data?
I was just answering in the Padlet.
Yeah, I see now.
And I was commenting on the use of artificial targets, but the question wasn't artificially generated by algorithms. We have not tested that. It would be very interesting to actually test. So if this is from someone that has a data set that we can test, we can actually proceed and see what is an artificially generated in situ data set.
Yes, it's not indeed super clear to me as well, but I think they are meaning indeed the synthetic accumulation done with the in situ verified spectral you know, contents that you can inject in the synthetic, for example, patches accumulation, windrows, fronts. That's what I think. So you think this could be also interesting for Ocean Scan in order?
I think it can be interesting for Ocean Scan, but we need to apply a validation criteria or a confirmation criteria. Like we need to be very clear on how confident we can be of a certain measure. So it is a matter of validating and performance and metrics, like to be able to be confident on that measurement in one way or another.
Oh, sorry, Laia. Indeed, the question is about not artificial targets, they replied, but synthetic data. So, okay, I think indeed, if these data, as you say, these data are somehow based on verified ground truths and maybe composed in order to make a large data set, they could still be interesting in order to launch artificial intelligence or even deep learning algorithm, as long as we don't have enough gathered in your database. Okay, thank you, Laia. You want to add something? Sorry.
No, it's okay. That I agree with your comments.
So there is a question to Caleb. I'm reading now. I watched your presentation regarding dam site detection, and I was wondering whether it would be possible to apply your algorithm for other areas across the globe, so Brazil, India, etc. What would it take to apply it for those countries?
Yeah, it's a very good question, and one that I'm also curious about the answer to as well. So we plan to expand the coverage of this algorithm, and so far the model shows a lot of promise to detect consistent forms of sort of open waste. But what always is the biggest challenge in expanding to new geographies is mostly in the negative class. If you think about it, we're detecting about 1 pixel in every 10 million or so is a waste site pixel. And so when we expand to new geographies, we're always, the model always gets confused by like some new weird thing that it's never seen before. And oftentimes the way that goes is we run a model in new geographies, evaluate the outputs, sample by hand in these classes that are sort of confounding for the model, and then the model generally kind of overall improves. So I think that it has a lot of potential to run in different countries, and Southeast Asia overall was sort of our first step in that direction by running a model that was trained just on Indonesia, specific data on broader Southeast Asia. So I'm excited to be able to expand it in the future. So in short, we're planning to expand it to run in new regions. And so far the model has shown to be it has the capacity to handle new regions, but always helps with additional training data.
Great, thanks, Caleb, for the reply. There is also an additional question for the same person, Philippe, from Brazil, indeed. What are the requirements for applying your algorithm? Is the code open and shared at some repository like GitHub?
It's not shared yet, but we do want to soon. Most of the reason it's not shared yet is because, as with any research code base, it needs to be a little bit cleaned up before letting other people in. But it's definitely the plan to be able to open source the code when we release that platform that I talked about at the end of the talk. And that should be kind of in the first half of next year. Or this coming year.
Okay, that's great. Excellent. I think there would be probably a lot to speak more, but unfortunately we are at the end of our session, so we will need to conclude right now. And we have 1 minute left, so let me take the chance, of course, to thank very much all of our distinguished speakers today for the important contribution to the session and in the field of remote sensing of marine litter. I would like to thank also the organizing team. There are several people behind the event, and in particular the Air Center that provided a great technical support towards the session. Special thanks go to Katarina, who is behind the control room, managing from Zoom to the chats to YouTube live streaming. So thanks, Katarina. And of course, I would like to thank you, all of you that joined and follow the session here and from the YouTube streaming channel. Before closing the session, I'm pleased to invite you to join our last part of the event, the part 3, today at 1700 Central European Time. We will present a preliminary summary of the outcomes and of the 3 sessions.